Last year I took an interest in perspective drawing, and I was like, hey, it'd be cool to use math to draw, and that led me to figure out a pretty solid method that actually makes curvilinear perspective a little easier, in my opinion. And I wanted to make this video because there's surprisingly a massive scarcity of information when it comes to curvilinear perspective. Even this complete guide to perspective remains incomplete when it comes to curvilinear perspective. So I'm hoping for this video to be like the definitive resource for curvilinear perspective. Quick disclaimer, this video is a bit math heavy, but I think anyone who has an interest in curvilinear perspective at all will still get a lot out of it. So let's get into it. If you've ever tried to learn about perspective drawing before, then you've probably seen people teach linear perspective. Linear perspective includes 1-point perspective, 2-point perspective, and 3-point perspective. But they're all really one and the same. The only thing that changes between them is the orientation of the camera, or eyeballs if you want to think of it that way. So right now if you pause the video, you'll see that straight lines come out of every single vanishing point radially, which is pretty neat because you can just put your points down on the page and then draw straight lines through all the points, and just like that you have a grid that you can use for your drawing. But low-key, it's kind of hard to draw in linear perspective. Let's go see why. I think the biggest hurdle for linear perspective is knowing where the vanishing points are supposed to go. Let's say our goal is to just draw a cube. Where do we put the vanishing points? They could go here, here, here. They could go anywhere. So where do we put them? Well, it depends on two things. To explain this, let's just put a normal looking cube on the page. Maybe it's supposed to be a table or a building or whatever. Now it might not seem like it, but just by drawing this one cube here, we've automatically set some important rules that the rest of the drawing is going to have to follow. So first of all, we can find the vanishing points by tracing the edges of the cube to see where they intersect. And now that we know where the vanishing points are, we can also see that the eye level line, or horizon line, has also been established. Now here's the thing, we didn't plan for the horizon line to end up there. That just happens when you draw something in perspective. And now, any new object is also going to have its vanishing points on this horizon line. But there's one more super important secret thing that's been established. And I think this often goes unnoticed in the art world. It's field of view. Field of view is an angular measurement of the observable area of your scene. It also happens to be one of the things that will affect the positions of the vanishing points. If I vary the field of view, you can see that it's basically just zooming in and out, right? But take a look at the vanishing points. They move! And the distance between them changes. For a higher field of view, the space between them decreases a lot. And for a lower field of view, the space between them is so big that they can even go off the page. Now if we keep the cube roughly in the same spot and size on the page, you can see how the FOV affects the cube. For a really wide FOV, the cube gets super distorted. And since the distance between the vanishing points is dependent on the FOV, this means that we can't really just place two new vanishing points wherever we want for any new object. For example, if we want to put another cube here like this, it just looks wrong, even though the vanishing points are on the same eye level. By the way, this distortion is exactly why a general rule you might hear is to keep the vanishing points far apart from each other, sometimes even off the page, which really is kind of an implicit way of saying that you should always keep a low FOV. In fact, I'd recommend like 60 degrees and below for linear perspective. But that kind of sucks because it means that we can't really draw everything that we can see. We're kind of forced into this little narrow section of our view. Like let's say that you were drawing this environment, for example, but you wanted to include some of the nearby stuff in the drawing. Well, that means that you have to increase the FOV, but that causes this horrible stretching. And to be fair, this might be the exact effect that you want, but I think that for most people it's probably not. But let's go back to our cube now. You'll notice that this cube has been rotated perfectly by 45 degrees about the z-axis. And yes, I am using positive z as the upward direction. Because of this orientation, we have like a corner view of the cube. But for a real drawing, you're probably not going to have everything oriented like this. In fact, you're probably going to have stuff in all sorts of orientations. And that's actually the second thing that affects the positions of the vanishing points. Orientation. If we orient the cube so that it's aligned with the world axes, then we can see that one vanishing point is at the middle of the horizon line. But where'd the other one go? Well, it's actually infinitely far off the page, which is kind of crazy. Now you might say, yeah, but it's easy because these lines are just parallel now. And I agree. It is easy for this special case, but we're probably not going to have this special case very often. And we've just shown that the distance between the vanishing points is not fixed at all in any way. A second ago they were both on the page, and now one of them is way off the page while one of them is right here in the middle. In fact, if we rotate the cube and track one of its vanishing points, then you can see it actually kind of behaves like a tangent function. It's roughly linear for small angles, but then it shoots out towards infinity for larger ones. And this right here is why rotating objects is one of the hardest darn things to do in linear perspective. Vanishing points could be literally anywhere, even off the page. So how do we draw anything if we can't know where the vanishing points are? I think for most artists, it's straight up just a skill that they build up through repetition and trial and error. But there are some tricks you can use to solve this rotation problem. Some people use a trick where they put another page next to their drawing, so that we can see where the off-page vanishing point is, and then you can just use a long straight edge to draw the object. But if we wanted even a slightly more rotated cube, then the vanishing point goes really far, really fast. So in my opinion, this trick isn't really that great. There's another good trick though. We draw an ellipse, which is really a circle in perspective, over the vertices of our object, and then we can mark where the vertices should end up for a given rotation. This is a pretty solid approach, but you have to be really careful using this method. Having the cube right here perfectly aligned with the middle makes it look really easy to use. But if we slide it over here, take a look at how the perspective affects the numbers. So the vertices on this ellipse won't end up on the same spots as they do on this ellipse. Which kind of sucks, because I'd imagine that most of the objects you're trying to draw are probably not going to be in the middle of the page. Now, to be fair, people have actually nailed down a solid workflow for drawing in linear perspective. They do it by doing the stuff that you see on screen right now. But come on, are we really going to do this every time we're drawing out in the field? And also look how small the picture planes are. We'd need huge pages and really long straight edges to do this properly. Now, curvilinear perspective isn't the easiest thing in the world either, but it does solve a lot of this stuff. You can control your FOV, there's way less ambiguity about the vanishing points, and we don't need super large pages. Now before we get into it, I want to give a few disclaimers. I'm not saying you should use one or the other. In fact, I think that in most cases, you will find that linear perspective is exactly what you should use. I just want to make this video to show a different approach to perspective drawing. Also, this method does require a little bit of knowledge of trigonometry, but it's basically just the arctangent function. I'm also assuming that you know the absolute basics of perspective. If you can draw a box using some vanishing points, then you're probably good. Also, to be clear, the stuff we learn about in this video won't automatically make you good at drawing. It's not going to teach you good line quality or shading or how to draw cool characters or anything like that. That stuff still takes practice. Alright, with that out of the way, let's go learn about this. The first thing we need to do is learn about the grid. Before we actually dive into using the grid, we should probably see where it comes from. Our big goal for this video is to look out into a real-world 3D scene and flatten it onto a 2D page somehow. And there's a lot of different ways to accomplish this, but we're mainly going to focus on the fisheye perspective version of this. From this moment on, we're going to be thinking in terms of spheres. Some smart people before us figured out a bunch of different ways to map images onto spheres by unwrapping the spheres so that they lie completely flat like this. A popular application of this is actually wrapping world maps onto globes. This right here is the equirectangular globe projection. All globe projections in general are basically just different ways of unwrapping a sphere, and there's a lot of them. But the one that we're going to focus on for this video is the azimuthal equidistant projection. This is the projection that produces that fisheye effect. And yes, it's also the exact globe projection that creates the map that flat earthers believe in. And no, I am not a flat earther, I promise. You're probably thinking, yeah, but we're not trying to draw a world map. Well, if I swap this map out for a 360 image, you might get a better idea of what we're trying to do. I know it looks kind of trippy like this, so let's move inside exactly at the center of the sphere. We can't even tell that this is the inside of a sphere anymore. It just looks like we're in this new environment. But we are indeed still inside a sphere. So all we really need to capture a scene is a sphere. Here's the big idea. We're going to use an imaginary sphere to capture a 3D scene, and then we're going to unwrap the sphere so that it can go onto a 2D page. We're basically turning ourselves into like a kind of 360 camera. Now take a look at this. If we draw lines along the straight edges in the scene, then we can see that some of them are actually curved. And if we keep drawing them more and more, we can find a point where they all converge. Let's also do this in this direction. And we can also do that in this direction. Are you seeing the pattern? We're drawing a 5-point perspective grid right now. This type of grid is what allows us to draw with that fisheye perspective I was talking about. But first we should learn how to actually draw the grid. I'm going to show you what I think is the best way to draw it, but you can draw it however you want. I start by drawing a circle around the midpoint of the page. I like to use a compass for this. This circle represents a 180-degree field of view. Now let's mark the vertical and horizontal axes. These lines are actually your eye level lines, and each spot where the circle and these lines intersect is a vanishing point. Although the top and bottom ones are off the page, but that's okay. We don't actually need to see those points, but you just need to know that they're there. Next, we divide the axes into halves. Now each of these marks are 45 degrees away from the center. Now to draw the curves for these 45-degree marks, I do it by kind of interpolating with these two segments. I'm not really trying to be precise in any way when I do this, I kind of just feel it out. So at this point, if you want even more resolution for the grid, you can keep subdividing the axes. So we can now make some marks for 22.5 degrees and 67.5 degrees. And you can keep dividing to get even more precise angles. But keep in mind that you're also going to end up making the grid look busier by doing so. By the way, you don't have to use these specific numbers for your axes. You can always measure out your own increments, but I'll leave that for you to figure out. So now we finished the inner circle. By the way, I didn't include lines of depth because they're actually straight lines coming out from the center. So I don't think it's that necessary to draw them. You can if you want, I just don't want to make the grid look busier. Alright, so if you've seen other 5-point perspective videos, you might think that we're done drawing the grid. But we can actually fill our entire page. So now, we'll interpolate between this curve and this axis. And then we can repeat that for the other sections. And then we can continue interpolating between those curves as needed. Everything outside the circle is beyond the 180-degree FOV. We also need to extend the curves from the top and bottom vanishing points, but since we can't actually see those points, I just eyeball it. It's no big deal. And now we're properly finished with the grid. Like I said earlier, if you did want to keep extending the grid, you're free to go all the way up to 360 degrees. But if we look at a 360-degree render, you can see how distorted some of the outer parts become. So if you want to avoid that super extreme distortion, then I recommend staying close to the 180-degree FOV. By the way, one interesting thing is that if we really narrow down the field of view, then you'll see that the grid effectively becomes a linear perspective grid, which once again demonstrates that linear perspective works best for narrow FOVs. By the way, you can download all my Blender files and stuff and mess around with the parameters yourself if you want. I'll also have a bunch of different grids available to download if you want them. See the description. Before we actually start drawing anything, there's something critical that you need to know. For this specific grid, meaning a 5-point perspective grid, it's critical that you face one of the vanishing points in your 3D scene directly. Usually you can do this just by facing a wall. Now I'm not saying you need to get close to a wall. You can be wherever you want, you just need to be facing perpendicular to the direction of a wall, if that makes sense. If you do that, then it means that you'll be facing the vanishing point. If you don't do that, then the grid won't work properly for your drawing. We'll see later on how to draw without actually having to do this. Now I'd actually recommend that you try to get comfortable with the grid, like just by tracing some basic shapes like boxes over it, on a separate page by the way. Just try to get a feel for drawing using the grid. You'll see it's really not that bad. Remember that your lines of depth are straight lines going through the center point of the grid. Alright, I think we're ready for the math. Remember that our goal is to figure out how to take a 3D scene and capture it onto an imaginary sphere, which we will then unwrap so that it's flat. How do we do this? Well, to get a better understanding, let's actually simplify the problem by making it 2D. How do we get a 2D scene onto a 1D page? Let's say that our camera or our eyes are right here. We're 2D beings looking out into a 2D world now, and we want to draw on our 1D page. Well, one of the ways that we can do this is by thinking of capturing the points in the scene on an imaginary circle around our eyes like this. And then we can unwrap this circle to make it a 1D drawing. All we need to know is how to capture the points onto the circle. And it turns out we can actually do this just by using angles. And then if we unwrap the circle, then it becomes a number line. So now all we need to know is the angle that a point makes with the horizontal for us to be able to plot it on the number line. And we can calculate this angle by taking the arctangent of the opposite distance over the adjacent distance. Using this method, we can plot any point in this 2D space. So now we can basically take any 2D scene and draw a 1D version of it. This is exactly what we want to do for the 3D case. Instead of using a circle, we're going to be using a sphere. And then we're going to unwrap this sphere using the azimuthal equidistant projection method, and then that's going to allow us to put it on a 2D page. So let's figure out how to do it. First, it's really important that we establish our coordinate systems. For the 3D scene, it's pretty easy. We're going to be thinking in rectangular coordinates. Basically, any point is represented by an x, y, and z value. One important detail is that the origin is positioned at our eyes. It is not on the ground. Everything is measured from your eyes. For the 2D coordinate system, we're going to be thinking in a kind of spherical coordinate system, but not traditional spherical coordinates. Usually in spherical coordinates, we use longitude and latitude, but we're not going to use latitude lines since they're not really that useful to us, but they will be later, so keep them in mind. With this type of perspective, the curves of the objects only follow longitudinal lines, both in the horizontal and vertical directions. So instead of longitude and latitude, we're going to use longitude and sideways longitude. I don't know if it has a proper name. In this coordinate system, each point is still represented by two angle values, but we're no longer using like an angle of elevation. Everything's going to be based solely on the horizontal and vertical axis that you see here. For example, this point right here is 45, 67.5. And this point is negative 33.8, negative 56.2. We should probably label the axes now. Since we're dealing with angles, let's call the horizontal axis the theta axis. And let's call the vertical axis the phi axis, or phi if you're a phi type of person. So if we want to plot a point, we just need a theta and a phi value. So we just need to figure out how to get these angles from a 3D scene. What we're going to do is calculate theta and phi by using trigonometry with estimated distances, just like we did with the 2D example. We know that the tangent of an angle in a right triangle is the opposite leg over the adjacent leg. So to solve for the angle, we can just take the arctangent of the opposite distance over the adjacent distance. So let's say there was a point here in the 3D scene. We'd probably be able to estimate that it's about 4 feet to the right, 5 feet forward, and like 3 feet below our eye level. Remember, everything's measured from our eyes. This gives us the rectangular coordinate 4, 5, negative 3. Now we can calculate the angles, which gives us phi is negative 31, and theta is 38.7. So we have the 2D coordinate 38.7, negative 31. And thus we can place this point right here on the grid. Now just for clarity, let's try to do a different point. Let's say there's a point 5 meters to the left, 10 meters forward, and 6 meters down. That gives us the rectangular coordinate negative 5, 10, negative 6. If we calculate theta and phi, we should get the following. And so we can place the point right here on the grid. And that right there is essentially how we use this point projection method. It's really just like a little 3D to 2D conversion. Now let's try to actually put this into practice and draw something. I made this super basic scene as like a little test environment, and I'm going to use this thing for every single drawing that we do in this video. We're going to do like 4 drawings in total. Since it's in 3D, it'll also let me show you the exact process for projecting points. I usually like to start by doing the corners of a room. So let's start with this point right here. I would estimate that it's like about 14 feet forward, 7 feet to the left, and like 5 feet above our eye level. Remember, everything is measured from our eyes. So we have the point negative 7, 14, 5. Now we can do our angle calculations, and that gives us the 2D coordinate, negative 26.6, 19.7. So let's go ahead and put that right here on our grid. Let's do another one. Let's do this point right here. We know that it still has to be 14 feet forward and 5 feet above our eye level, since it's like on the same level as the last point. but it is shifted to the right by like 8 feet. So we have the point 8, 14, 5. Now let's calculate the angles, and then we'll get the 2D coordinate, 29.7, 19.7. So we can go ahead and put that here on the page. Let's do one more point. This point right here, it looks like it's maybe 9 feet forward, maybe like half a foot to the left, and like 1 foot below our eye level. So we have the point -0.5, 9, -1. Now let's calculate the angles, and we get the 2D coordinate -3.2, -6.34. So we can put this point right here on our page. And so there you go. This is how you project points in 5-point perspective. Once you've projected enough points, you'll probably have enough information to just draw freehand. By the way, please don't try to move your points away from where you calculated. That's going to introduce error. If you really think it's wrong, then just try redoing the distance estimates and recalculate the angles. If you get the same angles, then you should place that point where the calculations suggest. We just don't want to introduce any kind of bias into these calculations. And there's our complete drawing. And now, since this is a 3D scene in Blender, I can actually render out what the final scene should look like using a fisheye camera. If we drew our grid and projected our points 100% perfectly, we'd have this exact image. And yeah, it's close enough, I think. So now hopefully you have everything you need to go out and actually try to draw in 5-point perspective. I don't think you should try to be perfect about this, by the way. I think this method should just be used as like a way to help point you in the right direction at the start. But I don't think you should go out there with like a measuring tape and map out every single point as accurately as possible. But I mean, it's up to you. And that's about it for 5-point perspective. But remember when I said that we have to be facing a vanishing point in the scene? Well, what if we don't want to face a vanishing point? What if we want to draw scenes at different angles? Well, then now we're in the realm of 6-point perspective. 5-point perspective is really just like a special case of 6-point perspective. It's exactly how 1-point perspective is a special case of 3-point perspective. Just a really quick aside, do we really need all these different names when they just refer to different orientations? I don't think so. But anyways, the grid changes if our orientation changes. For example, let's say you want to turn your body about the vertical axis. Then this is what happens to the grid. By the way, for these examples, I'm assuming that we still want to stay close to the 180-degree FOV, but remember that you can always go up to 360 if you really want to. I quickly want to mention one thing. Some people actually define 6-point perspective like this. It's two 180-degree FOV circles that are basically like two separate 5-point perspective drawings. And the purpose behind this is to show all the vanishing points, which basically shows the full 360 environment. One circle is facing the vanishing point in front of us, and the other circle is facing the vanishing point directly behind us. And I guess this is a valid way to define it. In fact, this is actually how 360 cameras store unstitched images. But I kind of disagree with this definition because it kind of implies that 6-point perspective is meant only for 360-degree field of view drawings. But that's not the case at all. You don't have to see all 3 points for it to be considered a 3-point perspective drawing. Similarly, you don't have to see all 6 points for it to be considered a 6-point perspective drawing. And we've already seen that 5-point perspective can handle a 360-degree field of view on its own. And this definition also just kind of closes us off to what's actually possible with curvilinear perspective. So for me, I'm defining 6-point perspective as what happens when we start with 5-point perspective and then we change our orientation in some way. Exactly how we just did by rotating about the z-axis here. You can kind of think of this grid as like the 2-point perspective version of 6-point perspective. I'm saying that it's like the 2-point perspective version because we only rotate about the z-axis. And I don't know if there's like a proper name for them, but I'm gonna call these grids Yaw Grids, because it's what we get when we rotate about the vertical axis, which is referred to as yaw in the context of engineering. But remember that we can also do the same thing about the horizontal axis too. By the way, you can draw yaw grids almost the same way that we drew the 5-point perspective grid. Start by drawing a circle, then put down your axes, although technically this vertical line is not an axis anymore. It's just like a normal grid line, but we put it there to help us out. And the top and bottom vanishing points stay in the exact same spots, but they're off the page, so just imagine them being in the same spots. But now, the other vanishing points will be in different positions. Luckily, we know that any vanishing point will always be 90 degrees away from its nearest neighbors. So we can actually place them at -45 and 45 degrees. But if we had only rotate by 20 degrees, for example, then we can just place them at -20 and 70. We just need to keep 90 degrees between them. Now we can put our numbers down like this. But where do we put them for these curves? I've always just eyeballed it and put 45 degrees kind of in the middle here, and then subdivided from there. But if you really care about accuracy, then you can actually use latitude lines to find the correct spots for the numbers. I just think that's too much work. Anyways, now we can interpolate the lines again to kind of feel out how the grid lines should go. And you can continue interpolating the curves to get higher resolutions just like we did with the 5-point perspective grid. And there we go, that's the final grid. So let's go ahead and try this grid on our test scene. Remember that this grid is for an orientation of 45 degrees about the z-axis. So we'll rotate the camera by 45 degrees, and then let's put it in a nice little spot like this. So once again, I like to start by projecting the points at the corners of the room. Let's project a couple of them together so that you can see how it works. If we look at this point, then we can say that it's like about 13 feet forward. And by forward, I mean approaching the vanishing point that the triangles are aligned with. We can also say that it's like 14 feet to the left and like 5 feet above our eye level. So that gives us the point -14, 13, 5. So if we calculate our angles, that gives us the 2D coordinate -47.1, 21. And we can go ahead and put that on our page right here. Let's do another one. This point right here is still 13 feet forward and 5 feet above our eye level, but now it's like 1 foot to the right. So we have the coordinate 1, 13, 5. And if we do our trig calculations, then that gives us the 2D coordinate 4.4, 21. So we can go ahead and put that right here on our page. Something that you should be aware of is that we can actually use this other axis over here. I'll call it the psi axis. The reason I'm saying this is that it can be kind of inconvenient to project points on the left side of the view when the triangles are aligned with the right vanishing point. To use the psi axis, we can actually align the triangles with the left vanishing point like this. And then we can measure points like this. Let's do this point right here as an example. It looks like it's like 11.5 feet forward. And again, when I say forward, I mean towards the direction of the vanishing point that the triangles are aligned with. It's 2.5 feet to the right and like 2 feet above our eye level. So we have the point 2.5, 11.5, 2. And now we can do the calculations, which gives us the 2D coordinate 12.3, 9.9. But you can probably see that our numbers don't really add up properly. This is because the numbers on the theta axis are actually based on the right vanishing point. So what we can do is actually just take our calculated theta and subtract 90 from it just to get the correct number. So the corrected coordinate is actually -77.7, 9.9. And then we can go ahead and put that down on our page right here. You got it? Let's do one more point just in case. This point right here is like about 3.5 feet forward, 3 feet to the right, and 2 feet below our eye level. So we have the point 3, 3.5, -2. So let's run it through our calculations, and that gives us the 2D coordinate 40.6, -29.76. And then we can subtract 90 from theta to get the correct coordinate, which is -49.4, -29.76. And that should go right here on the grid. And we can keep projecting as many points as we want until we start drawing by hand. And just like that, we have a complete drawing. So this is how you project points for a yaw grid. You know, for most of my drawings, yaw grids and the 5-point perspective grid have been the only types of grids I've ever really needed, but there's still a lot more possible orientations. For example, now, let's say that we were to pitch our neck down 45 degrees. Then we get this grid. Now this grid is a proper 6-point perspective nightmare. It's a lot harder to draw by hand, but we can do it. Don't worry. We do have to eyeball quite a bit though. This is actually one of those rare instances where we actually do need latitude lines. So let's go back to our yaw grid and remove all the grid lines. We can pitch down by 45 degrees by sliding the vanishing points along the latitude lines until they've all moved by 45 degrees like this. And this is where all the vanishing points are supposed to be. If we were only trying to rotate by 20 degrees, then they'd all just move right here. You got it? Alright. Now we kind of need to eyeball the triangle connecting the vanishing points. It looks kind of like that weird Mazda engine, where the edges are kind of round. Now we can actually extend the edges of the triangles outwards like this. Remember, we're just eyeballing all of this. Don't worry about being super accurate. But you know, like also don't be careless about it either. Now that we have the main axes down, we should write down the angle numbers. The bad part about this is that we don't really know where they're supposed to go, but we can get close enough like we did with the yaw grid. We know that each vanishing point is 90 degrees away from its nearest neighbor. So in the middle of each edge of the triangle, we can actually just put 45 degrees. And then we can subdivide kind of the same way we did with the yaw grid. So we can make marks for 22.5 and 67.5. For the outer parts, we kind of have no choice but just to guess where the numbers should go, but it's pretty easy to see just by looking at the trend. Now we have to draw the actual grid lines. So let's start by interpolating these two axes like so. And now we can repeat that same thing for the other part. Now take a look at these two curves. You see how they kind of curve in opposite directions? This implies that there exists a straight line somewhere in between them. So let's eyeball where this straight line is. Let's put it right here. And you'll notice that other parts of the grid are like this too. Now these straight lines actually run from a vanishing point and connect to its opposing pole. Not a neighboring vanishing point, but like the vanishing point on the opposite side of it, if that makes sense. So now, just like before, we can interpolate between all these curves to get more resolution. And just like that, we have a new 6-point perspective grid. You know, there's probably ways of drawing these grids perfectly, but it's probably more trouble than it's worth. And if I'm being 100% honest, I think it's okay to just print a bunch of these grids out and then keep them so that you can just reuse them forever. But it's also good to know how to draw them just in case. Anyways, now that we have the grid, let's try it out on the test scene. Remember that we pitched our neck down by 45 degrees. So I'll pitch the camera down by 45 degrees. And I'll actually move it up here to the corner of the room so that we have like a security camera type view. Projecting points basically still works the same way as we did with the yaw grid. Everything is just kind of warped a little bit now. Let's project a couple of points together. This point looks like it's about 13 feet forward, which again is towards the vanishing point that our triangles are aligned with. It's maybe 1.5 feet to the right, and it's 1 foot below our eye level. So that gives us the point 1.5, 13, 1. And we can run that through our calculations, and that gives us the 2D coordinate 6.6, 4.4. So we can put that point right here on our page. Easy. Let's do another one. This time let's use the psi axis. This point looks like it's 10 feet forward, maybe like half a foot to the right, and 7 feet below our eye level. So we can run that point through the calculations, which gives us 2.9, negative 35. Like I mentioned with the yaw grid, the numbers on the theta axis don't quite match up correctly since it's based on the right vanishing point, so we can just subtract 90 from our calculated theta. And that gives us the corrected coordinate, negative 87.1, negative 35. Let's do one last point together. Let's keep using the psi axis too. This point looks like it's 7 feet forward, 4 feet to the right, and 5.5 feet below our eye level. So let's take this point and calculate our angles, which gives us negative 60.3, negative 38.1. And we can put this point on our page right here. And once again, for your drawing, you can keep projecting as many points as you'd like. And there we go. There's the complete drawing. By the way, just for the sake of completeness, I'll also just quickly mention that you can also do roll rotations, but that literally just means rotating your page and drawing at an angle like this, so I didn't really feel the need to mention it at all. But it is something you can do. By the way, rotating the grid is exactly what you need to do if you were doing like a normal 5-point perspective drawing, but there happened to be like an object that was rotated differently. Any rotated object technically requires its own grid, but to draw a brand new grid every single time is kind of insane. So I recommend just trying to eyeball things like this. The good thing is that it's not as vague as linear perspective. If we want to rotate a cube by 30 degrees, then we literally just move its vanishing points by 30 degrees. How amazing is that? Even though we have to curve the lines a little bit, I think it's way more convenient doing it this way than trying to guess where the vanishing points are for a linear perspective drawing. Now you might be thinking, but aren't there infinitely many possible orientations? Yeah, there are, but you should be able to reach any orientation using the workflow I just showed you. Basically, any orientation can be achieved using 3 rotations: roll, pitch, and yaw. But like I mentioned earlier, roll doesn't really matter, because we can just rotate our page. Pitch and yaw do matter though. Let's say that we want to get to this orientation, for example. So step 1, we rotate our body left and right like this, and then step 2, we pitch our neck up or down like this, until we get to the right orientation. If you do it this way, then any orientation should be possible. But once again, I would just keep a couple of grids printed out so that you don't have to go through this trouble every time. There's one last thing I want to go over, just for the sake of completeness. Remember how I said that you can use pretty much any projection method to unwrap an imaginary sphere? I chose to focus on the azimuthal equidistant projection, because that's like the classic fisheye one. But another popular one is actually the equirectangular projection. This one's really good for drawing entire 360 panoramas, so I wanted to show you how to do this using this type of grid. So first let's figure out how to actually draw the grid. Since we want a full 360 panorama, we know that we're going to see every single vanishing point. So let's put the outermost 2 points down on the page like this. Now let's draw a line between these points, and this is actually our eye level or horizon line. Now we can actually measure the midpoint between these 2 points to find the center point, and this middle point right here is actually like the forward facing vanishing point. Theta equals 0 degrees. By the way, the 2 outermost points are actually the same point. Theta equals 180 degrees. Now we can measure the midpoints between these 3 vanishing points to get the remaining vanishing points. We have one at theta equals negative 90 degrees, and we have one at theta equals 90 degrees. Now let's go ahead and put some vertical lines passing through the vanishing points. Now we should put the numbers onto these axes. Let's start with 90 degrees. Technically, the correct way to do this is to keep these 2 lengths the same so that we can kind of form squares like this. But you can actually put 90 degrees wherever you want, really. Just make sure that the bottom kind of mirrors the top perfectly. And now we can subdivide everything like we did with the other grids. So we can put 45 degrees everywhere you'd expect, and then we can subdivide again with the 22.5s and the 67.5s. And you can keep subdividing as much as you want, but remember, try not to make it look busy. You know the deal. And so now all we need to do is draw the actual curves. The 45s are pretty easy. Just do it like this. Also make sure that you also draw the curves for the negative 90 and 90 degree vanishing points. These curves are actually supposed to connect to each other. And now we can interpolate these curves to get the inner curves. Now, the outer curves get a little weird. It's because we're interpolating with like this square shape right here, and this round shape. So what we need to do is kind of like still try to keep it curvy, but like it's kind of like trying to take on like a slightly square shape. I'm not being mathematical about this, I'm just kind of eyeballing it. Now we can repeat this for the bottom, and just like that we have a solid grid. Just remember that the z-axis grid lines are all parallel vertical lines, and they're like everywhere on this page. Alright, so I think we're ready for the test scene. This time, since we're doing a 360 drawing, I'm actually going to put our camera right here at the center of the room. This is just so that we can actually have everything in view. Alright, so let's go ahead and project a few points. This point right here, let's say that it's maybe like 7 feet forward, maybe like 8 feet to the left, and like maybe 3.5 feet above our eye level. And so if we run that through our calculations, then we get the 2D coordinate, negative 48.8, 26.6. So we can put it right here on our page. Let's do another one. This point right here looks like it's maybe 7 feet behind us, 5 feet to the left, and like 2 feet below our eye level. And so if we run the calculations on that, then we get the 2D coordinate, negative 144, 16. So we can put it right here on the page. By the way, with this type of grid, you can also do the thing where you choose a different vanishing point as the forward-facing direction for the triangles, but I'm going to leave that up to you if you want to do that. And just like I've been saying for all these other grids, you can keep projecting as many points as you want. And right there is our complete drawing. One really cool thing about the equirectangular projection method is that if we want to rotate an object about the z-axis, then we actually just shift the grid left and right. So like if we wanted to rotate a cube by 30 degrees, then we can just move the grid by 30 degrees, and then we can just use those grid lines to draw the cube. By the way, you can also pitch your view up and down with this grid, but I don't really see why you'd want to do that, since this is like more for panoramas, I would say, but I mean you can do that. If this all seems kind of hard to you, that's okay. 6-point perspective is probably like the highest peak in all perspective drawing. There's no shame in not understanding it, especially since there's like no good resources out there for learning it. In fact, most of the stuff that I talked about in this video, I had to figure out on my own. Well, not really on my own, I had ChatGPT. But my point is, I don't think there's any good resources online that explain curvilinear perspective. And I'm not even that good at it. I'm a freaking bad artist, dude. Why are you even listening to me? But at the same time, you should always remember that you don't need all this super complicated point projection nonsense. You can really get good at anything with practice. And I think that if you can at least draw a curvilinear perspective grid, then you're already like a good chunk of the way to having a cool drawing. And that's all I really have for you today. I hope you thought it was valuable to learn about this stuff. Maybe in the future I'll try doing videos where like I actually go through the process for like a real life scene. But I hope that I've given you enough to like go out and try this yourself. I really went all out for this video, so I would appreciate a like. And you can subscribe too if you want. I wish you the best of luck with your drawings.